which is primes, means that it has no other positive divisors except for itself and 1. Okay? Otherwise, it's not prime, and it's called composite. So the list of prime numbers, as you know, begins 2, 3, 5, 7, 11, and so on. Okay, there's the first 100 of them. 2 and 97 is the last prime before 100. Just for doing investigations and playing around with these, some relative MATLAB commands you might use are factor, which gives the prime factors of an integer, n, primes n, which returns, I think, an array or a vector of the primes up to the number n, and then is prime n, which will return true or false, depending on whether n is prime or not. Okay. So those are some of the relevant MATLAB commands you might make use of when you're investigating these things. And in 1 or 2 lectures' time, we're going to be proving this thing, which is called the fundamental theorem of arithmetic. And this is the main, or the key point about primes. One of the reasons why, or the main reason really why primes are important in the integers is it gives you a standard way of representing any integer. Okay, so we'll prove this theorem that every integer factors into a product of primes. So you can write an integer n. So p1, p2, p up to pr are all prime numbers, and they all occur to certain exponents in the factorization, p1 to the power alpha 1 and so on, p2 to the power alpha 2. We can factorize every integer like this, but more importantly, the prime factorization is unique up to reordering the way these things are written down. Okay? But essentially, the prime factorization of an integer is unique. An integer can't have 2 different prime factorizations. Okay? Where we count 2 factorizations as being different if they feature different primes. Obviously, given anything which has a lot of prime factors, you can write down this product in various different ways by shifting the factors around. But essentially, it only has the one factorization. So the set of primes is unique, and the powers to which they appear is unique as well. Now, again, it's tempting to think, oh, well, this is obvious. I know this is the way prime numbers work. You take a number 36, what's that, 4 times 9? So it's 36 is 2 squared times 3 squared. That's the prime factorization. Obviously, 36, you couldn't factorize it in any other way into primes. Maybe you can appeal to intuition like that for small integers. But, I mean, if you're talking about integers with 1 million digits, who's to say that there mightn't be 2 different representations of that integer with 1 million digits as a product of different sets of primes, okay? So, again, our intuition with integers really can only go so far as just the kind of integers that naturally fit. 1 million digit integers don't naturally fit our minds. Now, even we could already prove half of this. Just having the definition of a prime number, that's enough to be able to show that you can factorize every integer into a product of primes. Because it's like a recursive proof. You just take your integer and you ask yourself the question, well, can you factorize it? If you can't factorize it, then it's a prime and you're finished. If you can factorize it, you factor it in some way as a product of 2 integers. And then you say, well, are these integers prime? Do they factor? If they don't, then you've got a product of 2 primes and you've got a factorization, you're finished. If any of them is not prime, well, you factorize it. So just by iterating or repeating the definition recursively, you can prove that any integer can obviously be factorized into primes. So you just keep factorizing it until you can't do it anymore. And then the factors you have to be prime. What isn't so obvious and what we can't prove yet is the uniqueness. Okay? How do we know that a product of a whole bunch of primes can't equal a product of a whole different bunch of primes? we need to develop some theory, we need to develop some properties of primes that will allow us to prove that statement. So it's the uniqueness aspect of the fundamental theorem of arithmetic which really does require some proof. Okay? The fact that you can factorize every integer is really just a consequence of the definition of a prime number. If you can't factorize it anymore, then the factors you've got must be prime, and you're done. Okay? The problem is approaching or tackling the uniqueness issue, and it'll take us a little bit of development before we can prove that. So the proof of this is postponed till chapter 3, up to page 18. I'm running on page 9 at the moment, so we've got a bit of a way to go. So where do we begin? Well, we begin by coming back to divisibility, and so far we've only kind of talked about divisibility of a single numbers. But now we want to talk about pairs of numbers and how their divisibility might be related. So we're going to talk about common divisors. So definition 2.3, the top of page 9, well, it kind of is its own definition, a common divisor. A common divisor, C, of a pair of integers A and B. Common divisor just means that it divides A and it divides B. It's something which divides the pair of integers. Okay? So C is a common divisor of the pair A and B if and only if it divides them both. And then we single out a special common divisor. So any pair of integers might have many common divisors. For instance, 30 and 100. 30 and 100, 5 is a common divisor. 2 is a common divisor. Are there any other common divisors of 30 and 100? Someone's shaking their head, but there's still a few more. 10, yeah, 2 times 5. 1 is a common divisor. 1 is, remember, 1 divides everything. So 1 is always a common divisor of any given pair. You've also got -3 and -5, -10. Yeah. Now, we tend to, because divisibility, if an integer is divisible by another integer, it's also divisible by its negative and vice versa. So in our discussions, we tend to only focus on the positive integers. There isn't anything new, there isn't any new structure if we start talking about negative divisors as well. So most of the time when we're talking about integers and divisors and so on, we tend to just be talking about the positive ones. The multiplicative aspect or the factorization aspect of the negative integers is just a repetition of what it is for the positive ones. So we single out a special common divisor, and that special common divisor is the greatest such one. So the greatest common divisor of 30 and 100 is 10. It's the greatest number which is a common divisor of the two. Yeah. And we denote it by GCD of AB. So it's the greatest common divisor of the pair. So you can think of it as a two-place function, two-variable function. Some authors, if you look at some books, they use a very minimalist notation where they just do a bracket AB. It's a very quick notation. But we won't. We'll stick to using GCD because obviously it's a bit easier to read and it reminds you of what it means, and you won't go confusing it with a vector or something. Okay? So GCD is the greatest common divisor, also sometimes called the highest common factor. That tends to be a kind of a more school-based approach, I think. In mathematics, the term the greatest common divisor is the one that we use. So sometimes, now remember we said that 1 divides everything. So every pair of integers AB will have a common divisor 1. If there's nothing else that divides them. So if they don't share any factors at all, apart from the trivial factor 1, which is a factor of everything. So if their greatest common divisor is 1, then we have a special name for that. We say they're co-prime. So they may not be prime numbers themselves, but considered as a pair, they're co-prime to each other. So co-prime is a label you can attach to pairs of integers. The greatest common divisors always exist. Okay, for any pair of integers, as long as they're both non-zero, there will always just be a finite set of common divisors, so there will be a greatest one. And that follows from the well ordering of the integers. What happens if they're both, is there a greatest common divisor of 0 and 0? What's the greatest common divisor of 0 and 0? Well, in some senses, there isn't one because everything divides 0. So every integer is a common divisor of the pair 0, 0. But in another sense, so you could say the greatest common divisor of 0, 0 is undefined because there is no largest common divisor. But the usual convention is, and it's not really important, it doesn't really arise in proofs or arguments, but the usual convention is to say that the greatest common divisor of 0 and 0 is 0. That is sensible when you think about it, because remember, everything divides 0. So in a sense, it is the greatest common divisor. The greatest common, everything divides it. So 0 sits on the top of the hierarchy of integers in terms of dividing things. We usually think of 0 as being at the bottom, but because everything divides into it, the idea is if you follow a chain of divisors up, getting larger and larger, in a sense, sitting at the top is 0, because everything divides into it. But that's just for the sake of people who worry about things being complete and fully defined, you can define GCD of 0, 0 to be 0. Or you can just be happier in saying that, well, we won't ever be talking about the greatest common divisor of 0, 0. So I probably already spent far too much time on the issue. What's more interesting is taking a pair of non-zero integers and, worrying about or examining what their greatest common divisor is, because their greatest common divisor embodies what's common, what all the common factors between the two integers. In the next section, in the notes, we're going to look at something called the Euclidean algorithm, which is an algorithm for computing the GCD of AB. So given any pair of integers, it's an algorithm for computing it. And of course, you need some kind of a systematic way. For like small examples, 30 and 100, we can consider all the possible divisors in our head, and we can pluck the largest one out. But that kind of approach, that's not really much of a systematic approach to talking about huge integers. And also, it's not particularly illuminating to just say, given A and B, look at all the possible factors they have and obtain the largest one. It's all you're really doing is just checking the definition in a way. So the existence of the Euclidean algorithm as a quick, efficient algorithm for computing the greatest common divisor is interesting, and that's kind of what we're working towards at the moment. So we're going to start to develop the notation and the terminology to talk about the Euclidean algorithm. Okay. And what the core operation at the heart of the Euclidean algorithm is the operation of dividing integers with remainder. So just as in a Gaussian elimination, the core operation is row operations on the matrix. In Euclidean algorithm, the core process that you're repeating is integer division with remainder. Now, you're already familiar with this. You probably spent a large part of primary school mathematics, I know I did, doing integer division with remainder. So you have to say, 10 divided by 3, 10 is 3 times 3 plus 1. Did you all chant this in primary school, this kind of thing? 20 is 2 times 7 plus 6. So you divide an integer by another integer, it goes in so many times, and you'll have a small remainder. Okay, everybody familiar with that concept? Well, that's what we're going to look at. But, you know, this is university mathematics, so we chuck a load of symbols in and we make it sound more than it is. But essentially, that's what it is. So given any pair of integers, AB, this is theorem 2.2, what theorem 2 says is there exists a Q and R. Q is called Q because it's the quotient, and R is R because it's the remainder. So given any A and B, there exists a quotient and a remainder such that you can write the integer A as the quotient times B plus the remainder. Okay? The point about the remainder is that it's strictly smaller than the thing you divided by. So I said 20 is 2 times 7 plus 6. So the remainder is smaller than 7, the thing you divided by. It would sound perverse to say 20 is 1 times 7 plus 13. I'm kind of saying 13 is the remainder you get after dividing 20 by 7, but of course it's not the remainder because you could divide it again by 7. You could extract another 7 out of the 13 to leave behind the small remainder of 6. So the point, that's a key, very significant point about the remainder R. Okay, it sounds kind of a small, trivial point, but it's the key issue about it which produces the algorithm, which we'll see soon. Okay, so you can write A as the quotient Q times B plus the remainder R. Okay, now the theorem is saying that you can always do this, given any pair A and B, and you're not trying to divide something by 0, so B is non-zero. So the theorem is saying for every A and B you can do this, and moreover, you can only do it uniquely. So you can't divide you can't divide the integer A by the integer B in 2 different ways if you have this condition that the remainder always has to be smaller than B. There's only one way of doing it. Okay. And you can just have a quick look at how that's proved. That's proved by using the it follows from the well-ordered property of the integers. So this is what you've got in front of you in the notes. So we can appeal to the well-orderedness of the integers to get the existence of the pair Q and R. Okay? The way we do that is we consider the set S of all differences A minus Q times B for every possible value of Q. So we set S to be A minus, so I've switched to calling it T. S is A minus T times B for every integer T, and we're just considering the ones where this is positive. Okay, so if you like, S is the set of all the positive remainders you can get when you extract a certain multiple of B out of A. That's what S is. S is the set of all possible remainders after you remove a certain number of copies of B from A. Remember the well-orderedness of the integers, that was the alternative formulation of the induction axiom. The well-orderedness said every set of positive integers has a least element. Okay. That's not true, remember, of the rationals or the reals. Rationals can have arbitrarily small elements in it. But the thing about the integers is, any collection of positive integers, there's a unique smallest integer in that set. So here's a set of positive integers, non-negative integers, so it has the smallest element. And that smallest element we call R. It is going to turn out to be the remainder that we want. Okay, so we know that such an R exists because of the well-orderedness of the integers. Okay, and so therefore a Q exists, but we also have to prove that the remainder is strictly less than B. And we can prove that by a little proof by contradiction. So we know this R that we've identified is the smallest element in S, but if we suppose for a moment that it wasn't strictly less than B, if we suppose that R was greater than or equal to B, yeah, we've got this remainder R, which is a minus a certain multiple of b, and it's greater than or equal to the absolute value of b, well then we could consider this integer, r minus the absolute value of b. So you take the absolute value of b and you stick it on the other side. You've got r minus absolute value of b. This would then become here, you would be looking at a minus q and plus 1 or minus 1 times b, depending on whether or not b was positive or negative. If you consider b being positive, then this would be a plus sign here. Okay. The point about it is that if r is greater than or equal to b, then we can take another copy of b from the remainder r. And we'll get another remainder, which is non-negative. So we get another remainder here on this side, which again is a minus some multiple of b. And it's also non-negative, but notice that it has to be strictly less than the r we started off with, because it's r minus something. And the b, remember, is non-zero. So what we've produced is something smaller than r, which is non-negative, and which is one of these remainders. So we've identified a smaller element in S. That's a contradiction because this r was supposed to be the smallest one in S. Yeah? So S consists of all the remainders when you extract copies of B from A. By the well-orderedness of the integers, it has a smallest element. And now we've also proved it must be strictly less than b. If it isn't, that forces us to find a smaller element in S. But that's a contradiction because this r is the smallest one. That's where it came from. Okay. So we've now proved the existence of the pair q and r, the quotient and the remainder. So we can divide the integer a by the integer b. Then the other part of the proof is the uniqueness. Very often the uniqueness tends to come through okay here. So to prove uniqueness, well, you suppose it's kind of, again, a proof by contradiction, if you like, or maybe not phrased that way here, but we say, suppose we've got two pairs, a Q1 and an R1 and a Q2 and an R2 that both do the job, stated in the theorem. So A is Q1, A is Q1 B1 plus R1, and A is also Q2 B2 plus R2. So if they both satisfy the conditions of the theorem, well, by the proof we've just gone through, we know the two remainders have to be equal, okay? Because they're both playing the role of being the smallest element in that set S that we set up. Okay? So they can't both be different smallest elements. The smallest element of the set is unique. So R1 has to equal R2. If you look at the difference R1 minus R2 then, which is 0, but that can be rewritten Q1 minus Q2 times B. Okay, remember R1, yeah, that's just taking the equation A equals B1 plus R1. So R1 is A minus BQ1, and R2 is A minus BQ2. So when you take the difference between them, the A's cancel out, and you're just left with the difference of the two multiples of B. But then we're forced to the conclusion that Q1 minus Q2 has to be 0, because you've got this product equal to 0. And in this whole discussion, it's a condition in the theorem that B is a non-zero number. So you know B is a non-zero number. You've got a product of something with B being 0, so the other factor has to be 0. So Q1 must equal Q2. Okay. But that's that's kind of doing to death, really, this process that we were all introduced to in primary school. Dividing an integer by another with the smallest positive remainder. Okay? That's all it is. And that's the key operation that lies in the Euclidean algorithm, which is the algorithm for calculating greatest common divisors. Now we come to theorem 2.3, which is our first I think, our first non-obvious theorem. Think about it, the theorem 2.1, where we proved loads of properties of divisibility, none of them were surprising. The fact that, if something divides A and B, it divides every linear combination of A and B, and so on. Everything divides 0. There wasn't anything too surprising there. There wasn't anything too surprising in that integer division with remainder process, something we're quite familiar with. This theorem 2.3 is the first thing that strikes me as not being obvious. And even when I think about it now, it doesn't, I can't say I've got an intuition, about it that tells me, that it must be true just by thinking of the numbers themselves without thinking about the mathematics behind it. Okay? So what it says is that if we are talking about D being the greatest common divisor of A and B, the theorem says that you can always write that greatest common divisor as a linear combination of A and B. And moreover, well, it's not there in the statement of it, but it's apparent in the proof. D, the greatest common divisor, will be the smallest possible linear combination of A and B. If you're given any pair of integers A and B, you can obviously produce huge integers by taking linear combinations of something large times A plus something large times B. Right? It's kind of harder to produce small numbers. Okay, so you have to take you have to take a difference between a multiple of A and a multiple of B, and that might give you a small number. Well, this theorem says that the smallest positive number you can produce as a linear combination of A and B, that will be the greatest common divisor of A and B. That's the bit that kind of doesn't strike me as, I can't give you a pre-mathematical reason why that must be true. I haven't thought of it. Okay. So what was it? 30, we said the greatest common divisor of 30 and 100 was 10. So what's the linear combination of 130 that gives you 10? Well, it'll be 100 minus 3 times 30. These coefficients, the m and the n, are just integers. They can be positive or negative. So 10 is the greatest common divisor of 30 and 100. And yeah, you can write 10 as a linear combination of 30 and 100. It's 100 minus 3 times 30. And it's the smallest number you can write that way. If you experiment with other linear combinations of 100 and 30, you'll never get anything which is positive and smaller than 10. Okay. Now the theorem says that that smallest linear combination is the greatest common divisor. And this again is a nice proof which uses the well-ordered axiom of the integers. So it's again using this property which distinguishes the integers from other related number systems like the rationals or the reals. It's using the well-ordered property, which says, remember, every subset of positive integers has a smallest element. And it's also using the process of integer division with remainder that we just discussed. So you see neatly here how, things we've established already, we combine them to prove new results. Everything builds on what's come before. So how do we use this? Well, we a kind of similar approach to the previous proof. We consider the set S of all the linear combinations. Okay, so we're given a pair of integers A and B. We consider all of the linear combinations you could possibly form from them. And then we know, well, we consider all the positive ones, We know by the well-orderedness of the integers that there's a smallest such one. Okay? Here's a set of positive integers. It must have a smallest such one. So we call that smallest number D. And it will turn out to be this D, this greatest common divisor we're talking about up here. But what do we know about D at the moment? We just know that it is a linear combination of A and B. We know that it's bigger than 0, and we know that it's the smallest such number. We don't know anything about whether D divides A or D divides B. That's not known to us yet. All we know is that's the smallest such, it's the smallest positive linear combination of A and B. So how do we prove that it's a common divisor? Well, I mean, it could be a common divisor. Maybe it does divide A and does divide B, in which case there wouldn't be anything to prove. The theorem would be true. So we just have to do a little proof by contradiction to show that it can't, we'll prove it can't fail to be a common divisor. Okay. So if it isn't a common divisor, that means it must not be a divisor of at least one of them. So suppose, say, that D didn't divide A. In fact, we only need to go through the argument once, because we just repeat exactly the same argument for suppose it didn't divide B. Okay? So suppose that D wasn't a common divisor. Suppose there was one of the pair, A and B, that it didn't divide. Let's just consider that to be A. Well, if D is not a divisor, if D is not a divisor of A, that means we can run the integer division process, just like in primary school. A is Q times D plus remainder R. Okay? But we're supposing that D is not a divisor of A. So the remainder can't be 0. If the remainder was 0, then you'd have D dividing A. And there wouldn't be, it wouldn't be a problem. Okay? We're supposing D does not divide A. So then we have a non-zero remainder. We're using the theorem, it's the special smallest positive remainder, so it's strictly smaller than D. Now we're in the middle of a proof by contradiction. So immediately we're focusing on this remainder here, and we're going to extract a contradiction from it. We reorganize it, this equation, just stick the QD over the other side. So we have R is A minus QD, yeah. There's something, there's a couple of things we know about D. D is a linear combination of A and B. So just substitute that in. Replace D by NA plus NB. And then there's A is appearing in a couple of places, so you just tidy it up and you collect together all the A's. And then what do we have? Then we have this remainder R, and look, we recognize this, it's a linear combination of A and B. We don't really care what the coefficients are, something times A plus something times B. All we need is just that they're integers. Every object here is an integer, so the coefficient of A here and the coefficient of B, they're two integers. So R is a linear combination of A and B. That means it qualifies as a member of S, because it is strictly positive. So R qualifies as a member of S, but hang on, R seems to be strictly less than D. Well, that's a contradiction, because how did D arrive on the scene? D arrived because it was the least element of S. So we can't suddenly have stumbled upon a smaller element of S, R. That's a contradiction. D is the smallest element, not R. So then we worry that, the universe is full of logical contradictions and there's nothing but chaos in the world. That would be the case if things could be true and false simultaneously. A statement could be true while also being false. So it can't be that D is the smallest element and at the same time it has something smaller than it. Yeah? So what led to this apparent contradiction? What led to this apparent contradiction was this assumption here, that D did not divide A. So that assumption can't hold. Okay? If this situation here holds that D doesn't divide A, we immediately find a contradiction, a logical contradiction. So our conclusion is that this assumption can't be made. D must divide A. And for the very same reasons, D must divide B. There's nothing special about A. A is just one of the pair A and B. So you can rerun this argument and just direct it towards B. Okay? A and B are just a pair of integers. There's nothing to favor one over the other. Okay? So an argument along the same lines gives us that D also divides B. So this D, the smallest positive linear combination of A and B, it is the greatest it is a common divisor. That's all we've proved so far. It is a common divisor. The fact that it's the greatest common divisor comes from, this is the first time we quote theorem 2.1 property 3. It'll end up being burned in your minds. Theorem 2.1 property 3 is the divisibility of linear combinations. If something A divides a pair of numbers B and C, it also divides any linear combination of them. So we know that D is a common divisor. Why is it the greatest common divisor? Well, if you've got E, if E is any other common divisor of A and B, that E must divide D, because D is a linear combination of A and B. So any other common divisor of A and B, because A is a multiple of E, B is a multiple of E, but D is just a linear combination of these, so that means D is a product of E as well. D is a multiple of E. So this common divisor D we've identified is divisible by all other common divisors. So it has to be the greatest one. Okay? Because all other, it's a multiple of all the other common divisors. So D is the greatest common divisor. Any questions about that, or anything you'd like me to clarify? So tomorrow, well, where we're up to now is that brings us up to the end of that section. So there's a bunch of exercises 2.1 there. So those are proof-based exercises using the properties of divisibility and things like the greatest common divisor. So those will form the basis for some of our discussion next week. But tomorrow we're going to tackle the Euclidean algorithm. So I'd just like to look at an example of the Euclidean algorithm, just to finish today. So I compared it to Gaussian elimination before. Gaussian elimination takes a matrix and gives you a special matrix, a reduced matrix at the end of it, and it does so by repeatedly applying basic operation of row operations in the matrix in a sensible way to bring the matrix to standard form. Maybe it's not the best comparison, but Euclidean algorithm is the same kind of thing. Our aim is to take a pair of integers. Our aim is to get the greatest common divisor. And the way we do it is just by repeatedly doing integer divisions with remainder. And this is how it works. You take your 525. First of all, you divide it by the 90. So a class of 5-year-olds chanting 525 is 5 times 90 plus 75. You then take and it's kind of a visual thing, you then take the 90 and the 75 and you divide the 90 by the 75. You get a remainder 15. You then take the 75 and the 15 and you divide the 75 by the 15. You get a new remainder, a remainder of 0. And there the process ends. The output is the last non-zero remainder you had, which was 15. It turns out 15 is the greatest common divisor of 525 and 90. We'll explain why that is. Tomorrow, have I got the second example here? Yeah, here's a slightly longer example. 1, 2, 3, 7, 8, and 3054. What's their greatest common divisor? You divide the first one by the second one, you get a remainder. You divide the divisor by the remainder, you get a new remainder. You keep doing it. You keep dividing the thing you divided by the remainder. Eventually you get down to a situation where you get a remainder of 0. I haven't got the line, but 18 is 3 times 6 plus remainder of 0. the thing that you end with, the last non-zero remainder, is the greatest common divisor. Remember, I stressed the fact that in the integer division with remainder, the remainder was smaller than the thing you divided by. I said maybe it didn't seem that important to emphasize that, but that is a key emphasis. The fact that the remainders are getting smaller and that they're always positive, that's what guarantees that this algorithm or this process will always come to an end. Because the remainders are getting smaller all the time and they're always positive, so that means the process can't go on forever because you're heading towards zero and you're getting strictly smaller all the time. So you have to crash into zero at some stage. That's another key aspect of the integers. It's the well-ordered axiom again. You've got a set of positive remainders. There has to be a smallest one. Yeah. If we were working in the rational numbers, that process of getting smaller rational remainders could go on forever. You could get an infinite sequence of smaller and smaller rational numbers. But because we're talking about the integers, the process does end. So it is a genuine algorithm. You can tell the computer to do it, and it will terminate after a finite number of steps, which is the key property you need an algorithm to do. It needs to give you the answer, but it needs to give you the answer in a finite number of steps. Okay. So we'll discuss that in detail tomorrow. We'll look at these examples again. We'll do a few examples and we'll justify it, explain why it, I haven't said anything so far that justifies the fact that 6 is the greatest common divisor. Why is it that 6 is the greatest common divisor? Well, we'll talk about that tomorrow.